I'm Sudipta Das from Department of Physics, Vishwabharati Shantiniketan, and he is Nandan Roy from Center of Theoretical Physics, Mahidol University, Thailand. So we will be presenting a joint talk in this conference, Cosmology from Home 2022. First of all, we would like to thank the organizers for organizing this very nice and interesting conference. So today we will be presenting our work where we have studied where we have shown that one can study both the quintessence and phantom scalar field models. It is within a single setup, and we have used a general parametrization scheme for the Hubble parameter to study a model, to study a cosmological model. In this work, we have developed a setup in which one can study both the quintessence as well as phantom scalar field models at one go, and we have considered a general parametrization for the Hubble parameter through which we have studied this work. This work has been published in Physics of Dark Universe, and the archive reference is given here. We know that our universe is expanding, and it is expanding with an acceleration. The driving force behind this acceleration is known as dark energy, and lambda CDM, or the cosmological constant model, is considered to be one of the simplest candidates for this dark energy. This lambda CDM model, although it suffers from few drawbacks like the cosmological constant problem, which deals with the discrepancy in the value required by the cosmology and the field theoretical aspect. Apart from that, recently we have come across few statistically significant tensions which has emerged because nowadays we are technologically more advanced and we have a large number of data sets. What has been found is that the value of different cosmological parameters which are measured using the early data sets like Planck, WMAP, etc., and those values which are measured using the late time data like Holy Cow and Shoes data set, they differ in values. And those tensions actually tells us that one should look beyond the lambda CDM model. So regarding Hubble tension, we have taken these images from this reference. One can see that in the earlier years, when the data points were lesser, there was not much difference in the values which were suggested by both the early time data like your Planck, WMAP, etc., and the Shoes data, etc. But with the advancement in the technology, now there is huge discrepancy in the value of the Hubble parameter H0 for the Shoes data set and the Planck data set. The value which is suggested by the Planck WMAP data set is that the present value of Hubble parameter should be around 67 to 68 kilometer per second per meter per second, whereas the values which are suggested by Shoes and Holy Cow data set is that the value of H0 is much more, which is around 74 to 75 kilometer per second per mega per second. So there is a discrepancy in the value which is suggested by the early time data and the late time data. Another significant tension that has emerged corresponding to the lambda CDM model is regarding the value of this omega m, which is basically related to the structure formation of the universe. The value of omega m, which is suggested by the early time data, and the value which is suggested by the late time data like days and etc., there is huge discrepancy in the value of this omega m. So all these tensions or all these discrepancies, it tells us that the cosmological constant, it has some problem from the theoretical aspect as well as from the observational aspect. And so one should look beyond the lambda CDM model. The best alternative to lambda CDM model is basically the scalar field model because of its which are preferred because of their dynamical nature. This is the action for the scalar field, and this L phi corresponds to Lagrangian for the scalar field. This first part is the del mu phi, del nu phi. This corresponds to the kinetic energy part, and we have the potential energy part for the scalar field. What we have done is we have introduced a parameter epsilon here. We name it as the switch parameter, and this epsilon, we have considered that it can take values +1 and -1. For +1, it will represent a quintessence model, and for -1, it will represent a phantom model. Things will be more clear once we look at the field equations. So for especially flat and homogeneous FRW universe, the Einstein field equations that take this form. Rho m represents the contribution due to the matter density, and this rho phi corresponds to the energy density corresponding to the scalar field. Now, usually this rho phi, it is written as half phi dot square plus p phi. And but here what we have introduced this parameter epsilon, which we name as the switch parameter. And this epsilon, if it is positive, this will represent a normal quintessence matter. If it is negative, it will represent a phantom field because the kinetic energy part will then become negative. we have also considered that the matter sector and the scalar field sector, they conserve independently. So rho m is basically rho m 0 a to the power minus 3. It will follow its own conservation equation, and the conservation equation for the scalar field will be modified little bit because the switch parameter will appear, and so this is the modified form of this of the conservation equation for the scalar field. Now, using these two equations by simple algebra, by subtraction and addition, one can obtain the expression for h dot as well as one can obtain the expression for p phi. And if we perform this algebra, the expression for h dot, it comes out in this form, the expression for p phi, it comes out in this form. The next step is what we do is, instead of keeping it in the form of time derivative, the time derivative of this Hubble parameter h, we have converted it to the derivative with respect to the scale factor a. Similarly, phi dot, we have replaced it by the derivative with respect to the scale factor a. And if you put these expressions here, the expression for h dot, which now will be replaced in terms of derivative with respect to the scale factor, the expression for v phi, now we have written it in terms of this DDA of h square and so on. So all these expressions, one can write it in terms of this Hubble parameter h, the derivative of the Hubble parameter h. Next, what we have done is this h, we have just replaced it by the normalized Hubble parameter Ez, where Ez is h by h0, h0 being the present value of the scale factor. So all these equations, one can recast it in terms of the normalized Hubble parameter. And if we do this simple exercise, the value of the scale factor, the expression for the scale factor, the expression for the potential, they come out in this form. The detailed calculation is provided in our paper. Also, the various other relevant cosmological parameters, also one can write it in terms of this normalized Hubble parameter E of Z. So omega m, the density parameter for the matter field, the density parameter for the scalar field, the equation of state parameter, the deceleration parameter, all these cosmological parameters one can express in terms of this normalized Hubble parameter. Till now, we have not considered any assumption. We have just played around with the field equations. Now, from these expressions, one can think that as if the switch parameter epsilon is absent here, because one cannot see any switch parameter epsilon here. But actually, the switch parameter, the dependence of the switch parameter, it comes through this normalized Hubble parameter E of Z. Because if we look into this equation in the previous slide, what we have is this phi dot or this h, it actually contains this epsilon. So when we are finding the expression for E, the contribution due to the scale, the contribution to the switch parameter will be embedded through this normalized Hubble parameter E of Z. So all these parameters, although it seems that they are independent of the switch parameter, but actually it is not so. The switch parameter is embedded in this E of Z. So at this stage, we have obtained a general condition where one can find out whether there will be actually any phantom barrier crossing or not. So we have this expression for phi dot square here. And from this expression of phi dot square, one can see that we have a term like twice E dE dz minus 3 omega m0 1 plus z square. Same thing is for omega phi z. The equation of state parameter, one can rewrite it in this form. Now, this equation of state parameter, we find that the quantity which is inside this bracket, this quantity twice E dE dz and so on, this quantity, if it is positive, then this W phi, it will be greater than -1, and so we will get a quintessence model. But if this quantity is negative, W phi will be even smaller than -1, and we will lesser than -1, and we will get a phantom model. So we propose a general condition for this phantom barrier crossing, that when this quantity is equal to 0, suppose this quantity within the bracket twice E dE dz minus 3 omega m0 1 plus z square, it becomes 0 at some particular z is equal to z lambda. So any dark energy model for which this quantity is positive for z greater than z lambda and this quantity is negative for z less than z lambda, that means that that particular dark energy model will experience a phantom barrier crossing. The next is we consider a toy model for this particular model. So we consider particular parameterization for this h of z, which is basically polynomial in z. So this p, b, z, c, d, these are all model parameters, and this is a polynomial of order 3. So once we find h, obviously immediately one can obtain the expression for E of z. All the relevant cosmological parameters that has been defined earlier, that can be expressed in terms of these model parameters p, b, c, d, and etc. So these are the expressions. So this type of parameterization has already been studied in a number of models earlier. But the advantage here is that in our setup, one can study both the quintessence as well as the phantom scalar field model within this single setup. So the equation of state parameter, one can write in this form, where everything is expressed in terms of the scale factor A. This W0, W1, W3, these are basically dependent on this model parameters P, B, C, and D in this form. This W phi, if we try to find out the present value of this W phi by putting A is equal to A0, we obtain the equation of this form, -1 plus some quantity delta, and delta is basically dependent on W1, W2, and W3 in this form. So one can think of it as, for cosmological constant model, this W phi 0 is equal to -1. So one can think of it that this delta term is basically a deviation from the lambda CDM. And depending upon whether this delta is positive or negative, this will either give you a phantom model or a quintessence model. And this delta, it is actually dependent on the value of W1, W2, W3, or basically on this model parameters P, B, C, and D. So all other cosmological parameters one can express in terms of this W0, W1, W2, and W3, and this has been reproduced here. So all the cosmological parameters has been written in terms of this W0, W1, W2, and W3. So next we have compared the numerical and the analytical solutions, and this part will be presented by Nandan. So over to Nandan.
Hi everyone, hope you have been already convinced by the theoretical setup of our model. Now we move to the comparison of our model with the cosmological data. To do that, we have amended a publicly available version of the class code and implemented our model via the equation of state of a dark energy fluid. So now it becomes a responsibility to check that when we implement our model as a fluid in the class code, if it actually describes the scalar field dynamics. And to do that, we have compared both the analytical solution and the numerical solution, which we have got from the class code. And here is a comparison between the analytical solution and the numerical solution. For the analytical solution, we have solved the Klein-Gordon equation, and for in the class code, when we solve for the numerical solution, we have actually integrated the raw dark energy integration, which involved the form of the fluid. Here we can see that the match between these two solutions is within 1% of the percentage difference. So the fluid actually describes the scalar field dynamics. So in the next one, we use the cosmological data like the Pantheon, BAO, and SDSS, and we put Sue's prior together with the compressed Planck likelihood, which is a compressed version of the full Planck likelihood, and it has almost same constraining power as the full Planck likelihood. And one thing we must mention here that we have considered this parameter W2 to be 0 so that the class code run more smoothly and there is less shooting failure. But this consideration, this assumption does not put a very tight constraint on our model, because one can see that through this relation between P and D, one can always get a room for the viable cosmological model. And here is the priors. We have already considered a wide range of flat priors on both the cosmological parameters and the model parameters, and one can see here the constraint we obtain from the data analysis. And another thing we found that from the Bayesian evidence analysis, that our model is basically moderately favored over the lambda CDM model. And this is a kind of 1D and 2D posterior plot for the cosmological parameters. And this is the case for the model parameters. And one can see there is a upper bound for the W0 and there is a lower bound for the W1 and W3. And one can see that there is a slight increment in the Hubble parameter, in the current value of the Hubble parameter, but it is not enough to solve the Hubble tension. And here one can see that our result actually matches with these two findings in these two papers, and also our result agrees with this reference, where it has been shown that if you consider the CMB, BO, and supernova data, it put such a constraint on the H0 that you cannot pull the H0 to a higher value using the Sue's prior. So our result matches with the existing results. And here we plot the posterior probability for the the expansion rate of the universe and the equation of state and the deceleration parameter. And one can see that there is a phantom barrier crossing around z equal to 2.6 for our model, and the universe has entered an accelerated expansion phase from a decelerated expansion phase. And this is the 1 sigma. The dark blue is the 1 sigma and light blue is the 2 sigma region obtained from the Monty Python. And here we try to find the numerical evolution of the system by considering varying the model parameters W0, W1, W3 around the base field value. To do that, we have used this that we fix one parameter and we actually vary other two parameters. We fix one parameter to the base field value. Like the first one, we fix these two parameters to the base field value, and we change the W0 parameter. And here we fix W0 and W3 and change the W1. And here we fix W0 and W1 and vary the W3 parameters. So from this here, we can see that the equation of state is most sensitive to the W3, and it is least sensitive to the W0, which is shown here in this plot. And we have also shown the plot for the energy density parameter, and one can see that the energy density parameter does not vary much with the vary of the model parameters. And here we show the CMB anisotropy for the same set of parameters which I described before, and we found that at the higher L and lower L both there is a shift from the lambda CDM model at this bottom panel, so that at both the higher L and the lower L, we have a shift from the standard lambda CDM model. And here we show the plot for the matter power spectrum, and throughout the whole scale for all the three cases there is a constant shift from the lambda CDM model. So to conclude with what we have done, we have revisited the dynamics of the scalar field dark energy model, considering both a general setup for the quintessence and the phantom scalar field, and we are able to write down all the cosmological parameters in terms of the Hubble normalized Hubble parameter, present matter energy density, and the redshift. And then we actually try to find out a general condition for the phantom barrier crossing, and we did the data analysis, and we found that this model actually cannot solve the Hubble knot tension, and there is slight deviation from the lambda CDM model for pK and the matter power spectrum from the lambda CDM. So one should, for the completeness, one should consider the perturbations also while studying this model. And another thing is that this the model we consider shows moderately favor than the lambda CDM model. So with this, I would like to thank everyone for listening to my talk, to our talk. Thank you.